I think we're now on take 3 or 4 or something like that. So what I want to do is I want to explore how either the irrationality of the number affects arithmetic dynamic properties or how to get the swivel camera to swivel. One of them is going to be easier for me to do than the other, so I think I will concentrate on the mathematical one. All right, so famous theorem due to Dirichlet. So alpha irrational implies n alpha mod 1 is dense. So again, when we talk about equidistribution, it means it falls evenly. Before you can get something at that level, ask if you can do something weaker. Can we just prove that if you give me any point in 0, 1, we approach that infinitely often? And so what that means, just formally, is here's 0, 1, you give me any x, you give me any epsilon, and I can find an n such that n alpha mod 1 is within epsilon. And of course, by taking epsilon to be small and small and smaller, I can construct an infinite sequence of n's that will have this property. The equidistribution is then whatever interval I take, the fraction of the time I get there is equal to its length. With many things in life, that's just the beginning of the subject. After you get the main term, that the time I'm in the interval AB is b minus a times the number of indices n I've looked at, the next question is how large is the error? What's the scale of the fluctuations? And typically you might only get maybe a savings of a logarithm, or if you're lucky, maybe get a savings of a power of n. The greater savings you get, the more you can say. Which do you think is going to have better behavior in terms of being equidistributed? Something that's very irrational or something that's not so irrational? And of course, we need to quantify what we mean by how irrational. So we'll say you're more irrational, the better you can be, the worse you can be approximated by rationals. Or the better you can be approximated by rationals, the closer to rational you are.
Well, probably the more irrational you are, the more efficient you are.
Yes.
Because especially we know that one approximation like Benford's law is that rational number ratios tend to result in 1 with 30%.
I'm not quite sure about the connection with Benford at the end, but I do agree that the more irrational you are, the more equidistributed you will be.
When we say approximated by rationals, is that a topological?
So no, and so there's actually two different notions. So what we typically mean is if I look at alpha minus p over q, by choosing the denominator q to be sufficiently large, I can do a really good job approximating alpha by a rational p over q. It's not that impressive. You want pi to 100 decimals? Sure, take q to be like 10 to the 100. The challenge is to get a really good rational approximation using a small value of q. And so we often measure the cost of a rational approximation by the size of the denominator. Yes? So typically what we want to do is we want to quantify how good is the error in terms of the denominator. So what we could do is we want this to be less than or equal to some constant over some function of the denominator. So if this function here is cubing, or if this function is to the 10th power, cubing is not going to be nearly as good as to the 10th power. The 10th power would be far more accurate. Now, of course, just because I have a bound that it is less than or equal to c over q to the 3, it might actually be less than c over q to the 4, q to the 5, q to the 6. I don't know. That's just an upper bound. So for some of these things, you might also want a lower bound. And so what we're going to do in Dirichet's theorem is we're going to show that this holds infinitely often. So infinitely often, we can approximate alpha at least this well. Now when we're doing something like this, do I have to assume p and q are relatively prime? What do you think? But what if I chose not to consider p and q relatively prime? I'm not going to discriminate today. It's a weird day for me. I'm going to treat all rational ratios equally. Is it possible I could have this infinitely often where p and q share common factors? So for instance, I could have this, maybe p naught q naught, then I could have 2 p naught over 2 q naught, 4 p naught over 4 q naught, 8 p naught over 8 q naught. What if I did that? Could that hold infinitely often? Okay, why not?
Like, because you can get any small, like, on the right-hand side.
Right, because the denominator here would have to be getting smaller as well. And so if I keep just multiplying q by higher powers of 2 and the numerator by those same higher powers of 2, I haven't changed how good the approximation is, but I've now changed this number over here. So I'm not going to have infinitely many p and q that are just multiples of the same starting value. So without loss of generality, I will assume p and q are relatively prime. And again, when you're trying to measure the cost of something, you really don't want to take into account common factors. If you're measuring things in terms of the cost of the denominator, and the denominator and the numerator have a common factor, remove that common factor. Okay, so the question is, why is this a good metric? Well, it seems to make sense if you think about it that the size of the denominator is related to how complicated the rational approximation is. The bigger it is, the more options you have, and the better job you should be able to do with the approximation. So if I look at all denominators with 5 digits and all denominators with 20 digits, I will not do worse if I give myself more digits to play with. Worst case scenario, just use the smaller value. So you're not going to get a worse approximation by letting q get larger. The question is, how much better will you get, and how will you find the best approximations? So there's a well-developed theory on how to find these best approximations. And the method is to use something called continued fractions. So the continued fraction expansions talk about how to find this. And they also talk about the most irrational number. Anybody know what the most irrational number is? Most irrational. And it's a very famous number.
So in this case,
The one that's hardest to approximate by rationals, where your error is the worst possible. At least one person in this room has written a paper involving this number. The most irrational number. Any guesses?
it's not E because that's.
It's not E. And you want to take a guess?
Is it phi?
It is phi. It's the golden mean. Phi is 1 plus root 5 over 2. And when you write it as a continued fraction, like this, it turns out the larger digits you have in here, the better approximations you get when you truncate. So the worst possibility is when you have all ones. So in fact, when you're trying to approximate an irrational with a rational, the golden mean is the hardest. And I think what you get is it's less than or equal to 1 over square root of 5q squared. And you can improve the constant from 1 to square root of 5, to 1 over square root of 5. If you stay away from the golden mean, you can do a little bit better. But the golden mean is the worst. Okay? So for a lot of problems, the better I can approximate my irrational with rationals, the more I know. Okay? And in fact, we can, yes?
Why does having all ones make it most rational?
It just turns out when you truncate the continued fraction expansion, that gives you a rational p over q. And the smaller numbers you have here, the slower things are going to grow and the worse your error is going to be. So it's not immediately clear, but if you're interested in stuff like this, it's chapter 7 of the book. Question?
No question is that, okay, well, I get one of the ones to make it harder to approximate.
Right.
Like, I would assume there's other numbers exist or have that has the same property. Why exactly is it specifically that hard to approximate?
Well, I mean, any other number is going to have at least a 2 somewhere.
Really, any of them?
Well, the only number that's all ones is, unless, of course, I replace this one with a 3 or 4 or 5. If I add an integer to the golden mean, it's essentially the same number, because I just increased the numerator by a couple of multiples of q. So you typically assume your number is between 0 and 1. This number is not between 0 and 1, but
Is there a topological related thing? So if you suppose
I don't want to get into the topological thing now, but later that is something to look at. There's different ways to talk about the sizes of numbers. There's the cardinality approach, there's the measure approach, and they do give you different answers. So I want to keep that on hold for now, but
I'll ask you later.
yep. So this is just a real quick introduction. All right. So the camera is not swiveling, it's still not swiveling? No. So I'm going to essentially confine myself to this board. Okay? So if you have not copied anything down or not copied down enough today, I apologize. But it should be hopefully available later. All right. So what I want to do is I want to prove Dirichlet's theorem. So proof. So consider xn equals n alpha mod 1. So we get the numbers x1, x2, x3, x big Q, x big Q plus 1, and we fix some big Q. Okay? So I have Q numbers. And if I look at the interval 0, 1, I can split it up into boxes of size 1 over Q. All right. How many objects do I have? Q plus 1, and I have Q bins. So this is Dirichlet's pigeonhole principle, Dirichlet's box principle. If I have n plus 1 objects and only n places to store them, at least one thing must have 2. So we have to have at least 2 of them in the same bin. We don't know which bin it is. So let's say maybe here's kq and k plus 1q. And we have 2 different things going in here. Maybe we have xn and we have xm. So xn mod 1 and xm mod 1 are in k over q, k plus 1 over q. So they've got to be very close to each other. What this is going to allow us to do is it's going to find some integer multiple of alpha that's going to be really small. It's going to be less than 1 over q. So imagine I can find an integral multiple of alpha that's less than 1 over q. So maybe it's 1701 alpha mod 1 is less than 1 over q. Then what I do is I keep adding 1701 alphas. And every time I add another 1701 alphas, I move at most 1 over big Q. And so I just start walking down the real line. And you give me any number, each time I increase by 1701, I move at most 1 over big Q. So as long as 1 over big Q is less than epsilon, I can't jump over the number I'm trying to get. And I will be able to walk and get close to anything. Okay? So that's where we're going with all this. So we know that these 2 numbers are close. So what this means is it means n alpha minus m alpha minus some integer L. How large must that be? So how large would n alpha minus m alpha be when I subtract off the appropriate integer? How far apart are they? I'm sorry? So how far apart is n alpha and m alpha when I choose the appropriate integer L? 1 over q. And so you have to choose the right value of q. Well, I know that xn is an alpha mod 1. So if I subtract off some integer from this, I'm in this interval. If I subtract off some integer from this, I'm in that interval. I just combine things with L. So this is going to be less than or equal to 1 over q for some L. And what this then means is alpha minus L over n minus m is less than or equal to 1 over q, I'm sorry, it's 1 over n minus m times big Q. How big can n minus m be? What's the largest n minus m could be?
Q plus 1.
think you can do better than q plus 1. I'm not saying you can do much better than q plus 1, but I think you can do a little bit better than q plus 1. Bless you. It has to be what? Smaller than 1. Well, these are two integers.
Yeah. Oh, that's a number.
Right. So q plus 1 is just a little bit too large. Why are you saying q plus 1? It's at most q, right? Not a big improvement, but a slight improvement. Because I'm choosing my numbers from 1, 2, 3, all the way up to q plus 1. They can't be the same number, so their difference is at most q. How small could it be? I'm sorry? It can be 1. They can't be the same number, so it's at most 1. So in fact, this is less than or equal to 1 over q squared. And here, I'm going to let q be n minus m, which is less than or equal to q. So we've just shown that we can find integers. L is going to be our p, n minus m is going to be our q. And the difference between this is going to be at most 1 over q squared. So we can get very close to 0. Now the problem is, unfortunately, and this is a subtle point that is often overlooked. The danger is, what if little q is small? Right? We were trying to show that this is really close to 0. Because if this is really close to 0, we can then just march down the interval. Well, maybe q is like 2 or 3, and this is 1/4, 1/9. That's not good. We're trying to show that it's small. So is everybody comfortable that we showed that this is true? But the difficulty is that this might not be small. Fortunately, we know that this will eventually get small. I can't always have little q being small. Eventually, little q has to grow. Why do I know little q has to grow? This is often not covered in standard presentations of this. So this is the value added for today. Yeah. Why do I know that little q has to be growing?
Sorry, when you say eventually.
Well, that I can form infinitely many p and q. So here, L will be my p, n minus m will be my q. And so this is alpha minus p over q. And I want to claim that I can do this infinitely often, and that I'm not going to get every single time q equals 2 or 3.
So then the idea would be to show that as n increases, n can't increase as fast.
Well, it's not n that increases. What's the thing that what's my original free parameter?
Alpha.
Not alpha. Alpha's fixed.
Oh, q.
Q, big Q. I let big Q get very, very large. Not only is this less than or equal to 1 over little q squared, it's less than 1 over big Q. What does this tell you about the size of little q? How small can little q be? See, little q is less than big Q. So this whole thing is going to be at most 1 over q squared. Did I put this in the wrong way?
You substituted a little q for a big Q, so that's right.
Little q is smaller, so I made this thing bigger. But we also know that this, I'm sorry?
Well, if q equals n minus m, which is less than q, n minus m equals to be 1, then you can at least be 1, like the smallest one.
The smallest little q can be is 1. If little q is 1, we're in trouble. Because if little q is 1, that means we don't have that good of an approximation. So we know that this is at most 1 over little q squared. The danger is if q is always taking on values like 1, 2, 3, or 4. We don't want that. We want little q to be growing.
It's at least root q.
So why is q at least root q?
Because q squared, because we know it's at least, n minus m is 1, so we know that it's at least 1 over q. And so if we're writing that in terms of little q, then little q
As we have a little room over here, I think, to play with, yes. So we have 1 over big Q. We have, well, let's be very careful. We have Q times big Q is less equal to 1 over Q squared. Right? So unfortunately, we cross multiply, we just get back again Q less than equal to big Q. That doesn't help us and tell us that little q is growing. Yes?
Wait, is it something like that we're in 0, 1, so there's only so many fractions with small denominators?
Okay, that's going to help us a lot. So there's only so many fractions with small denominator. So if q is always at most 100, then we know we can't be more than a certain distance away. And then eventually, that 1 over big Q is going to be smaller than that. And so eventually Q has to grow. So that would work. Okay? So that's one way around it, is we know if little q is bounded, there's only finitely many possibilities. They're never exactly equal. If they were exactly equal, alpha would be rational. And so eventually we will be fine. Okay, so that's one way to approach it. The other way to approach it is to say, screw it. It's a technical term. We don't really need the 1 over q squared for what we're trying to prove. We just need that this fraction, alpha minus p over q, is small. I don't really care what little q is. As long as it's at most 1 over big Q, that's fine. Choose q so large that 1 over big Q is at most epsilon. And we've got a rational approximation that's really close. So either way works. I like the thing that Blake was suggesting because that means we know little q is going off to infinity. Okay? So there's a lot of stuff going on here. We now know that given an irrational, we can approximate it with rationals at least as well as 1 over denominator squared. We can do this infinitely often. We can do this with the denominator going to infinity. Okay? Any questions on what we're doing? Yes?
Never mind.
Okay. So what I'm going to do now is I'm going to erase this. And I'm going to say if we took this expression, if we multiply through by n minus m, we would get q alpha minus L, and I'll call LP, is going to be less than equal to 1 over big Q. We could also get it, it's 1 over little q, but this is fine. This is more than enough for us. And so that tells us every time we take an extra q copies of alpha, we move at most 1 over q modulo 1. And so now what we want to do is you give me an x, you give me an epsilon, choose q so that 1 over q is less than epsilon. We could actually choose it to be less than 2 epsilon as we walk. And then there's two possibilities. The first possibility is q alpha is now between 0 and 1 over big Q like this. And if that's the case, then every time we increase, we move at most 1 over q, and we can't jump over this whole set. And we have to be within epsilon of x. So you give me an x, you give me an epsilon. We choose a big Q so that 1 over q is at most epsilon. You could do 2 epsilon if you want. If q alpha is now a small positive number mod 1, every time I go q alpha, 2q alpha, 3q alpha, I won't see the next one, you keep walking like this, you have to walk within epsilon of x. If instead q alpha was not very close to 0, but very close to 1, you would just be walking backwards. And it's a very similar argument. So this gives you denseness. Right? This is a lot of work for denseness, but okay. Any questions on what we've done so far? This holds for any irrational number. This is extremely nice. But there's a lot of stuff we do not know. We don't know anything about equidistribution. We don't know about how often, which is related to equidistribution. We know that it's at most 1 over q squared. Maybe it's better. Maybe some numbers are better than others. So I know some of you are looking for research projects. I want everyone to try a research project in this class. The fact that pi squared is irrational implies that there is infinitely many primes. I have one of the worst proofs using the irrationality of pi squared to try to quantify how many primes there are at most x. So initially, this just seems to tell you that if there weren't infinitely many primes, there'd be a contradiction. We'll see this when we start studying the Riemann zeta function. You can use how well you can approximate your number by rationals to get information about how many primes there are. The problem is, I'm trying to prove a weak version of the prime number theorem. The way we know how irrational pi squared is we use the prime number theorem. So by using the prime number theorem, which says there's at most x over log x, there's about x over log x primes at most x, I can prove there's at least log x primes. So this is not the greatest proof. But if you really open up the proof of the irrationality of pi squared and how well you can approximate it, you don't really need the full strength of the prime number theorem. People just used it because, well, we know it. And so if you want to try to use this approach to try to estimate how many primes there are, it's possible. And if anybody wants to do this as a research project, let me know. I've got some extensive notes on this that I would love to see brought to fruition. Again, I want to see you guys doing research projects rather than just doing homework assignments. And so I know some of you are still looking for things to do. Okay, any questions on this? So depending on how interested you are in stuff on this, I'll let you think about it. Lots of other things we can do. One of my favorite theorems is Liouville's theorem. I think we do that in chapter 5, but I'm not positive. I'd have to check. That says if you are too well approximated by rationals and you're irrational, you must be transcendental. And this is actually a way to construct not only infinitely many, but uncountably many transcendental numbers. And so if you're interested, that's something we can do, yes? So a transcendental number is a number that's not algebraic. And an algebraic number is a number that's not transcendental. Does that help? Okay, if you had said yes, I would have, okay, good. So an algebraic number is a number that solves a polynomial of finite degree and integer coefficients. So the square root of -1, the square root of 2, square root of 2 plus square root of 3, these are all algebraic numbers. It turns out algebraic plus algebraic is algebraic, algebraic times algebraic is algebraic. Everything else is transcendental. Pi is transcendental, E is transcendental. In fact, almost every number in 0, 1 is transcendental. And this is where we can get some differences between measure and topology. If you look at the measure of the rational numbers, it's a measure 0 set. If you look at the Cantor set, the measure of the Cantor set is also 0. But the Cantor set has uncountably many numbers. So from a topological point of view, from a cardinality point of view, the Cantor set is in some sense as rich as the entire interval 0, 1. But from a measure theory perspective, it's much worse. It's much, much lower. So depending on your notion, you get very different answers. So if people are interested, that's definitely a topic we can do. This is a great way to prove numbers are transcendental. You've got to be extremely well approximable by rationals. Very few numbers are going to be easy enough to analyze directly. And I guess just for completeness, I will write one of those numbers. So these are called Liouville numbers, or Liouville's number. I guess we'll do a specific one. The sum, n goes from 0 to infinity, of 1 over 10 to the n factorial. So this is a great number. If I truncate it after n equals 100, the next term is 1 over 10 to the 101 factorial. It is significantly smaller than the denominator I just kept. These numbers are extremely well approximable by rationals in terms of the denominator up to that point. Okay. Any questions about this stuff right now? So what I want to do is I want to talk about a research project. So I was talking with Professor Goldmakher after the colloquium on Wednesday, which was a nice talk by Lily on Ramsey theory. And so, Ramsey theory is concerned with how large must you be before a certain structure emerges. So no matter how I assign things, no matter how evil I try to be, I cannot prevent certain patterns from emerging. So the standard one is the party problem. So how many people do you need to have at a party before you are guaranteed either 3 people all know each other or 3 people do not know any of them, any of the 3 of them? So this is considered now in 21st century America Facebook friends, because you cannot be friends with somebody if they're not friends back with you. Whereas in the real world, it is quite possible to consider yourself someone's friend and they do not consider you their friend. How many of you have heard of love triangles? Yeah, to me, it's not really a triangle. It's a line segment with an isolated vertex. But it's unfortunate notation. And there was one of these structures going on when I was in graduate school. It led to impeachment hearings during President Clinton's impeachment hearings. It was somewhat amusing that this was going on in graduate school, but
That's only one part. You could also have love cyclic graph, right?
you could, oh, there's lots of things you can do I will leave that as an exercise to the undergraduates. You probably just talk amongst your friends and get lots of different shapes.
Love binary tree.
Binary trees. So here is the question. And so the reason I want to do this is an open research question. It is way too hard for you guys to solve. And if you think I am not adequately giving you credit for your ability, please prove me wrong. But what I want to do is I want to take this as a springboard, and I want to try to find questions we can solve. And I want to just brainstorm with you as to how do you generate research projects. So some of you probably know that I run research groups at Williams over the summer. And I tend to take a few more students than some other people. And this requires me to have a lot of research projects available that are interesting, that the mathematics community will care about, and are accessible to students with different levels of background. And so one of the real things you need to learn is how do you generate good research projects? Well, a lot of times as you see what people are working on, and you try to see, is there a special case that might be interesting and accessible? And so here is the question. Paint the positive integers red and blue. Are there x and y such that x plus y and xy are the same color? Can you force that to happen? So I have not checked. I am assuming Professor Goldmakher was not lying to me when he told me that this is an open problem. How should we try to solve this?
Are there restrictions in the way you
So basically, the devil is painting. Yes?
And also, like we find operations, I mean, what if, like, if x is red and y is blue, what would x plus y be?
You get to choose whatever color you want x plus y to be.
Really?
You're painting. So if you're having trouble thinking about how to paint, you can come to my house and practice painting my house just to get some practice in painting. I'm happy to provide that service. So let's look at the integers. 1, 2, 3, 4, 5, 6, 7, 8. And maybe we'll assume x does not equal y. Yes?
Do these operations have to give?
You are painting the integers. You're painting the positive integers. You paint them any way you want. Is there a way to assign the colors so that there's never a pair of x, y where x plus y and x times y are the same color? Yes?
I mean, can x equal y?
I'm going to assume for now x does not equal y.
Oh, okay.
Yep.
So there's never a pair. Like,
Right. So I mean, for instance, if you color all the evens blue, it's not that hard to show that it works. So the question is there a way for me to be evil? What color is 1 going to be? Red. Why not? Okay. So this is red. What about 2?
Maybe another red.
Okay, at this point, it could be red, it could be blue. There's no problems right now. 1 times 2 is 2, but I don't have to worry about anything. So at this point, we don't know what color it is. So if you want for now, we'll assume red. What about 3? Why does it have to be blue?
otherwise 1 times
But 1 times 2 is not 3. Okay. Oh, that's fine. 1 times 2, okay, would give me a red. Okay, so here we have to color this blue. Okay. What about 4? So 1 times 4. Wait a minute. When we did 3, when we did 3, we have to do x plus y and x times y. I don't think we know that 3 has to be blue.
Well, 1 plus 2 take 1, 2 be your x and y. 1 times 2 is red. So blue is a...
Oh, I'm sorry. We're getting 3 from 1 plus 2. I'm sorry. I was looking at it as multiplication. Sorry.
You can do the same thing and argue that it has an alternate.
Okay, so now what's 4 going to be? 1 plus 3. Okay, so 1 times 3, that's blue, so we would have to color this red.
That means, yeah, but that means it has to
Eventually you can.
Okay, now the next one, what's 5 going to be? 1 plus 4, and then 1 times 4 is, so this has to be blue. So hopefully by induction we can show we go all the way down. Do we get an issue here?
Yes.
Okay, do we have the issue already?
Yes.
Okay, what's the issue?
The issue is at least,
Issues that all you... Sorry.
the issue is at least at 2, 4, 8.
Okay,
Yeah.
so,
Yeah, 2,
Around 2, 4, 6.
well, 2, 4, like, all the units.
6 and 8.
right.
2 times 4 would be.
Okay, so we have a problem here. Well, maybe the problem was we made this red. And so maybe this should be blue. And so we can go back and we can now try to see what would happen if we made that blue. Okay, there's another way to try to deal with a problem like this, is to say, this is not a good problem, because I can do something stupid. What stupid thing am I doing? My kids call that the S word. What stupid thing am I doing in this problem that's causing us a lot of heartache? Which number is having a huge impact? 1. So one possibility is to say, I want this to hold not just once, but infinitely often. So maybe 1, do infinitely often. Or 2, only color the integers that are greater than or equal to some big N. And I don't care what's happening in the very beginning, I only care about the structure in the limit. So again, when you have small behavior like this, it could be the case that you need to go pretty far down before the true behavior emerges. So in a lot of problems in number theory, later we might get to these when we do the circle method, how many ways are there to write a number as the sum of a fixed number of squares or cubes or fourth powers? It might be that for small numbers, you have a little bit of a problem because you don't have enough flexibility with all the squares. And it might be from some point onward, every number can be done, but in the beginning, there's some problems. We believe every sufficiently large even number is the sum of 2 primes. What does sufficiently large mean? Greater than or equal to 4, right? 2, there's not quite enough room to write 2 as the sum of 2 primes. We actually now have as a theorem, and one of my colleagues from grad school is the one who put the final nail in the coffin. We know that every sufficiently large odd number is the sum of at most 3 primes. Actually, it's the sum, I think, of exactly 3 primes. What does sufficiently large mean?
The least number such that for all numbers after.
What's the greater than 5, 7 or higher. And if your number is 5, there's just not enough room to write 5 as the sum of 3 primes. So conditions like this are really natural conditions. I want to talk about other ways to generalize this. So one of the ways that I was talking, after Professor Goldmakher showed me this, I said, okay, are there x and y such that this is true? Let's look at a new variant of this. So we're going to paint positive integers red and blue, maybe from some point onward. And we're going to fix an r greater than or equal to 2. And what we want is the following. There is a set x1, xr such that at least one of xi plus xj, I does not equal j, equals xl times xm, L does not equal m. So what we were doing before is we just had two elements. And we said x plus y had to be x times y. Now I'm going to allow myself, I just want one of the sums to be the same as one of the products. Do you think this is easier or harder?
The objective is, again, to find a painting such that it never...
Is either to prove that there's a painting such that this never holds, or to prove no matter what coloring you choose, it has to hold. Do you think this is easier, as difficult, or harder?
Harder, there's more things to check.
I only need one element of the sums to equal one element of the product.
No easier.
It can't be harder, because the other one's a special case. This has more things. It might be of the same level of difficulty. I doubt it, because I have more things at my disposal. So I believe Professor Goldmakher and I proved that there is a value of R such that this will always hold no matter what coloring you have. So this is the Goldmakher-Miller constant. All right? As long as R, you win. Can color. So one thing is for you to prove the Goldmakher-Miller constant does exist. Try to find a bound on it. Here, what's the smallest R I need for this to be true? What are other generalizations you could ask? What else could we look at? So here, I was saying I want to two-color all the integers from some point onward, such that if you take a set of R elements, at least one of the sums and at least one of the products is the same. What else could I look at? Yes?
You can also hand color the...
We could end color, right? Maybe there's more than two colors in the world. Maybe not all of mathematics is black and white. There could be shades of gray. Okay. So what if we now have other colors? So can you prove maybe, we'll say we have C colors. Is that finite? And then can you have some idea of how big that must be as a function of the number of colors? Do you think it's going to grow as you increase the number of colors? You know, how many I you need? Do you think it'll stay the same size, or do you think it'll get smaller? Could it get smaller? No, it can't get smaller. It might not grow, but it's definitely not going to get smaller. All right, so that's one question you could ask. What's another question you could ask? This is how you generate research. The original problem is way too hard if I can trust my junior colleague. We'll check on that later. And for his tenure cases, I really hope none. Well, if one of you disproves this really quickly, this will give me some. All right. What else could we ask? So I'm looking at sums here and products here. What else could I ask? Different operations. And then what would be good choices of operations to do? You could do differences. You could do sums and differences. We have to worry about quotients. We could do exponentiation. Lots of different possibilities.
Is it trivial, not trivial, but is it really, one of the thoughts that I had was LCM and GCD, but does that end up getting you into trouble really fast?
Well, you could try something like that where you have a set of objects and now you only have one element or two elements associated to it. I have this set and I associate the least common multiple and the greatest common multiple. I also have maybe arithmetic means, geometric means. But now with something like that, I might leave the integers. So you've got to be careful. So maybe I want to work in some kind of ring. Maybe I want to work in the rationals. Maybe I want to expand this and look at vectors, look at lattice points in two-dimensional space. Maybe I want to work with matrices and talking about adding matrices and multiplying matrices. So the whole idea is to generalize something, to create lots of new problems from a given problem. And that's why I wanted to spend a couple of minutes talking about this. If anybody wants to work on this, this would be, I think, a fun project to work on. I think there will be definitely accessible results. I am trusting my colleague, I've known him for a long time, that when he says the original problem is too hard, I will trust him. But maybe we can get some information from some other problems. You can then also start asking, what % of the time do you have a collision? If I color, let's say I look at all the integers up to x. What fraction of the pairs, what fraction of the triples have a collision? Is it a positive %? So again, there's a lot of questions you can think about for something like this, and I encourage you to try to do that. Okay.